to, no point in recording that now. So you guys are just joining us. You have 4 minutes of silence. Maybe that's the best way to watch my videos, is to not hear my voice. I'm gonna have to start putting them through like one of them voice things. Make them all sound different. That would be the best way to go. Because, God, again, I think I sound awesome in my head, but I've listened to my stupid videos. They're terrible. I've got, like, in this room, like 15 different microphone things to try and make my voice sound like I think it sounds inside my head. And I've used them all at different times. They're all terrible. Just terrible. But all right, let's get back to work here. I think we can all agree we've got 200 newtons downwards for the sine and another 50 newtons downwards for the boom. That's pretty easy. The cable's pulling at, I don't know what the angle is, but it's got to be that way. Right? You could probably figure out the angle. You guys are smarties. I mean, I say that knowing that in the last class period, I did have to kind of suggest to people how they might find out what that angle is, and that hurt my feelings. And so I know right now there's some of you who are slinking in your chair because you're saying, yeah, I needed to know that. And now you understand why it was bugging me that it took people so long to figure out the angle, because they left their calculator in radians, had no idea why we were getting the numbers we were getting. All of these things, terribly frustrating to a guy like me who's like, is that really where you are? This stuff can be hard enough if you can't figure out how to put your calculator in the right thingy thing. Oh, wait, sorry. Owen has a question. And that's a good question. And I did not explain that in sixth period, but yeah, I'm going to the dot today because I know that we have off-axis forces. Now, here's the thing. This is not balanced, right, as it is. If we were to let this go, it would not be balanced. So obviously the wall is applying a force to the boom as well. I mean, it's going to have to be pushing this way. There's not a doubt that it's got to be pushing that way. And I'm going to call that a normal force. But the wall probably is not just pushing outwards. And there's no way to know this next part without just some experience. But the wall is probably pushing at an angle one way or the other. Because truthfully, our natural pivot is probably here. And because our natural pivot is there, this thing's either spinning this way or trying to spin this way, and the wall has to prevent that from happening. I guarantee if you hang a mass on one side of a meter stick and you pinch the middle of the meter stick, it's going to spin, and that's what this is. So the wall's either preventing this side from scraping upwards against the wall or scraping downwards against the wall. You need to pick a direction for the direction that the wall is acting on the boom arm. I'd like to break this up into two forces because I feel like the idea of the normal force is obvious, but the wall could be doing upwards or downwards on it, and it's hard to know. Now, in this one, it's not hard to know. I'm choosing upwards purposefully. Pick a direction. When we work the problem out, if the force from the wall is negative, then you pick the wrong direction. But pick a direction. And I would encourage you to break the wall up at the start of a problem like this into a normal force and then an up or down force from the wall. You will understand a little more as to why to do that as this progresses. But I just find it to be easier. Now, we can do net force on this. We're going to have to. We had to yesterday as well, so let's do net force on this. I have net force in the x direction, that has to equal 0. And net force in the y direction, that has to equal 0. I'm going to apply a coordinate system. And I'm going to label that theta. You'll have to get theta. I do not want to, do sine of the inverse tangent of 1 over 1.5. You guys should probably figure out what that angle is. But I'll let that be you. I'm just going to pursue theta for now, because I will be sad when somebody has the wrong value for the angle. So let's start with recognizing I think that this is going to have to be t cosine theta. And then I'm going to have something over here that's going to be, well, it's going to be, I don't know how big that's going to be. We'll say like that, t sine theta. I'm feeling like I don't have to draw the whole triangle in there. We've gotten past that. It's all that first semester stuff. So x direction, I'm going to have normal force equals t cos theta. I think that's pretty good for the x direction. It's the y direction that's got more stuff in it. In the y direction, we're going to have, let's see, force from the wall plus t sine theta minus 200 minus 50 equals 0. That look good, Donovan?
Would the force from the wall be friction?
It depends. I mean, if all you did was back to work. We can't do anything here, right? Way too many unknowns, and only 2 equations. So we're gonna have to move on. Let's do the torque side. Torque side is gonna be the thing that'll do it. You have to choose a pivot point, and here's where I hasten to tell you what to do. Except there are some choices that are better than others. I said to put the pivot point at a place that would eliminate one of your torques. That suggests 2 different places, here and here. Now, I think we want to get the tension. I think the tension is a necessary thing here. In fact, that's my goal, is for us to figure out the tension. If we eliminate the tension by putting our pivot point there, we're going to generate an equation that has at least one unknown, right? The force from the wall. The normal force doesn't apply a torque because of its direction. You follow me? But I really would prefer to get the tension in the cable. I think that's the big winner here. So I'm going to recommend for most boom arms, you put your pivot point here and make that your fulcrum. Now this suggests that we're going to have 3 torques. There's the torque from the boom arm itself, its center of mass. There's the torque from the cable, and then there's the torque from the sine. I see 3 torques. Those torques are going to have to sum to be equal to 0. I am providing you with scaffolding, a manner in which to organize yourself. Do it whatever way you want, but I am providing scaffolding. That's the fancy technical education term that they don't use anymore. That term was all the rage, like, I don't know, 15 years ago, 12 years ago. There's been so many of these stupid terms that have come and gone. I think right now the terms are just hate on your teachers, but there were times where we had all these cool terms. Now, I set this up for you because we know every single torque has 3 different components to it, right? Size of the torque arm, size of the applied force, and the angle at which that torque arm and force are at each other. So let's start with the boom arm itself. We know that the torque arm distance is 1.5 meters, right? Center of mass of the boom arm will be at the middle of the boom arm. And the force is the weight of the boom arm, that's 50 newtons. And I'll draw this in, but the weight's downwards, and our boom arm is horizontal, so sine of 90 degrees. Bless you. We good? All right, we got to choose if it's positive or negative. That's right-hand rule. Right-hand rule. I saw somebody fail miserably. Look, did you draw this picture in your notes? All right, then take it and turn it so that the fulcrum is close to your chest, but the arm extends outwards. If you're having trouble doing this, then look, I'm going to help you once, but after this, I'm going to think you a bit of a fool. And I don't want to. So if you've done what I just asked, then look, the force of gravity points either to your left or your right. And a torque arm goes away from you. So it's going to be either you're putting your hand this way or this way. Look at your picture and decide. For me, Torque arm is this way. And now I leave my finger pointed away from me, and I have to rotate my finger until my middle finger is in the direction of the force. It's R cross F. My thumb points away from the board. So that's the direction of my torque, away from the board. That's the positive direction. It's a positive torque. The curl rule tells me that that torque is trying to make this boom arm travel counterclockwise. If the cable were cut, that's going to be the direction it'll rotate. So, all of that to say that this has to be positive. Moving on to the cable. It also is affixed 1.5 meters away from the pivot point. We have an unknown amount of tension there. And we'll need this angle. Or this angle. Take your pick. We need one of them. I bet that is the result of the inverse tangent of 1 divided by 1.5, which 33.7 degrees, I'm pretty sure.
Yes.
Oh, yeah, I know. I say pretty sure just for funsies. But it is me trusting sixth period. But I did do it on my own calculator, and I got that number, so I'm okay with it. A positive and negative. I'm going to do the whole same thing again. This one might be a little weird for you, but this way, that force is like this way, but over here. But notice, it doesn't matter where this finger is. My thumb still points into the board. It's defining a plane. It's either out of the board or into the board. What you don't want to do is have your hand like this and say, oh, I can do that and get it. But now my thumb's out of the board. If you do this, you're doing it wrong. Very clear about it. This only. Now flip me off, you have to turn your wrist. Okay? So we have to go like that. Then we're okay. This is into the board. That's negative. Negative. All the way. Don't be negative. Be positive. Last one. The sign is hung 3 meters away from the edge, and it has a weight of 200 newtons acting straight downwards. That's 90 degrees. We good? Positive or negative? Come on, it's positive. It's trying to cause the boom arm to travel in the same direction as the weight of the boom arm is. There we go. Add them all up. 1.5 times 50, that's 75. Minus 1.5 t sine 33.7 plus 600 equals 0. This will provide you with the size of the tension. You should figure that out. All right, 811 newtons. It's 811 newtons. Guaranteed. Concerned you guys need your calculator to tell me this, but I'll wait. So, I'll just kind of put this at the center here. The tension in the cable. Are you aware of how much more tension there is than stuff being held? I mean, look at it clearly. The sign and the boom arm together are 250 newtons. A range like this, the tension in the cable is more than 3 times the weight of what it's holding. This might not be the way to go. People just think stuff will work out because they can mount it like this. Do you see why this is a problem? You better use the right cable here. This has to be some stuff. If you buy cable that's tested to be able to lift 250 newtons, you'll be sad when you set this up. Because you need cable that's more than 3 times stronger than that. But a lot of people don't realize it. They'll jump up, grab that sign. Funniest home video right there, right? I got the heavy cable. Let me tell you a little experiment about leverage. Because there it is. Now, you should be able to tell me whether the wall is pulling up or down on the boom arm. That's your next job. Is the wall pulling up or down on the boom arm? We know what the tension is in the cable now. So force of the wall plus 811 sine 33.7 equals 250. What direction is the wall actually pushing or pulling on that boom arm? You got it now? What's the answer? Negative what? What's that? Wow, that's a nice solid mumble.
200.
Thank you. This means we made a bad choice, right? We made a choice. We said it was upwards. Math says it's downwards. So that means the wall must be pulling downwards. Notice how much, almost the full force of the whole thing. You see that, right? I'd argue that this arrangement might not be the optimal arrangement. Now, look, it's a boom arm problem. So if we're talking about physics for just a minute and solving stupid little physics problems, manipulating this makes a big difference, doesn't it? Because that's going to change that angle, and changing that angle makes a huge difference. Clearly, changing the leverage is going to matter, and changing where this is mounted is going to matter too. All of these things contribute directly to how this is going to operate. And that's what these problems are going to be about. You guys have had a little bit of optimization too, some of you. Do you understand that this, if you're really going to build stuff, optimization is all over this? So if you have a range in which you're trying to keep your system within, optimizing for that range is appropriate. Now, I see all of you getting very agitated. Clearly, that means that we are close to a moment. But two, I want you to think about what level 3 must be. This is not level 3. This would just be another level 2. Like if I wanted to walk on one of these suckers, you know what I'm trying to, what I'm thinking this is? Make a ladder, angle it against the wall. How many forces act on the ladder? 6. I mean, there's the obvious ones, right? The ladder and the person standing on it, but that floor better push up on it, and you better hope there's some friction on it. Pretty sure the wall's pushing this way on it, or else you're sliding. And I bet there's friction one way or the other on the ladder too.